A lot of interesting stuff happens in the hallway. It happens, you get to walk out of a session and there's a collective experience that you just went through. And so there will be a hallway conversation that springs up discussing the material.
First of all, a wonderful good morning. And welcome to this installment of the Back to Basics track, which is about algorithms. So, a few words about myself. I'm doing C++ trainings, consulting, etc. And actually, algorithms is one of the topics I really love to talk about, because it is an example for just good software design. And so this is just a perfect fit for the Back to Basics track. So, it all started in 1994 with this paper. A paper entitled The Standard Template Library, proposed by Alexander Stepanov for standardization in the standard library. And in this paper, he proposed what we today all know as first the containers. Perhaps the interesting detail about the containers is that the containers do not contain a lot of algorithm-like functions. So algorithms, the second component, are actually free functions, completely separate from the containers. And there was a very specific reason to do that, because this allows this entire library to be extendable. Yeah, from a design point of view, this is nice. Yeah, so imagine you have a container and you want to add another algorithm. You could not add anything to standard vector. It needs to be something outside. And the algorithms, on the other hand, they should not be bound too strongly to the containers. Of course, they should work on all containers, even if you add a new one. So these concerns are perfectly separate. Good. But they need to work together, and this is what we, of course, do by means of iterators. Iterators is the abstraction level in between, and this is how they work together. Now, on this level already, this looks a little bit like a toolbox. So all of this stuff works like little things that you could put together. And this is one reason why I like to talk about this SDL stuff and the algorithms, because this is just good software design. This is how software should look like. And I know, it looks like playful stuff, child's toy, but it's actually really, really useful. Now in this talk, we're going to talk about algorithms only. Unfortunately, this year there's nothing on containers, but there's another talk on iterators. So if you wait till 2 p.m. Today, Nicolas Süters will talk about the other part, the iterator part. And you get a little more of a complete picture. All right, so let's have a little bit fun with algorithms and the Simpsons. Yay! Okay, I see there are not a lot of Simpsons fans in the room. It's probably too early, I know, but we'll have a little fun with the Simpsons. So let me introduce the cast for this talk. First, we have Lisa, the algorithm expert. Then, of course, on the other side, we have Bart, the totally algorithm-ignorant skeptic. And, of course, we also have Maggie, the always interested C++ enthusiast. So let's first introduce a little struct person. So persons have first names, last names, and an age. Super simple, not really something to go into. And we introduce an entire vector of persons, the Simpsons. So we have, of course, Homer, Marge, Bart, Lisa, and Maggie, the Simpsons, but we have also a couple of other characters from the show. So Hans Moleman, Ralph Wiggum, Milhouse Van Houten, Ned Flanders, Jeff Albertson, Montgomery Burns, and potentially many, many more. Yeah, imagine that this is a vector of, say, 50, perhaps even more Simpsons characters. Good. Now, let's do something with this vector of persons. Bart has a first idea. Let me find the youngest person in the vector of persons. All right, so how can you do this? Well, first, officially, we should check if there's actually a single person. So if this is an empty vector, there is nothing to really do. Okay, else. We first pick the first element as the youngest person. Why not? It's a first good guess. But then, of course, we go through all the other persons. And we note this one, this little detail. We go to the kind of second element, and from there till the end in single steps. And we compare the age of all the persons. Yeah, if the age of any person we are currently at is smaller than the age of the currently smallest person, youngest person, then we found a new youngest person. And you do this until the end, and then we have found the youngest person. Great. Who is the youngest person? Well, in this vector of persons, it's of course Maggie. But Maggie totally disapproves Bart's solution. Now, she really doesn't like that for many very good reasons. First, this is hard to read. Now, I don't know which code you usually read, but I would definitely argue this is not easy. You really have to scan through all of these little details until you really understand what's going on here. So it's hard to understand too. And now this is one single slide of code. Okay, it's not a lot. But imagine this on a big scale. Yeah, programmers, developers scanning this kind of code every single day. How many hours are lost due to that? And how many bugs are introduced when now somebody wants to add a little other detail? This is innumerable. This is really, really bad. It's also very verbose. Okay, as I said, it only fills a single slide, but still, it's a lot of code for this simple problem. And it's easy to get something wrong. Really, I pointed out a couple of little details, like the +1 here, the comparison, the ++. Little details, something could go wrong. And last but not least, in this form, it definitely is not reusable. Maggie disapproves. Maggie is not happy. Now, Maggie actually would use, okay, last comment here. The comment itself basically shows us that there's something wrong. Find the youngest person. If you have to explain to developers what the next piece of code is doing, something is wrong. Now, Maggie would use an algorithm. So she goes to CP reference, and so immediately on the start page, you actually have a link to all the algorithms. It's right there. Right column, third from top. And when she clicks on that, she comes to the algorithms library page. A huge page, really a huge page. This page contains, probably don't believe it, more than 200 algorithms. 200! But we don't have to go through all of them. That definitely is not really an option. We are now looking for the youngest person in a vector. Of course, there's no algorithm called youngest person, but if we generalize this a little bit, we realize that we are looking for a minimum. And there's an entire category of minimum, maximum algorithms. What we're now looking for is this particular algorithm, min element. It says so right away. It returns the smallest element in a range. So if you go to any of these algorithms, you'll find a lot of details. Yeah, for beginners, this is sometimes indeed a little scary because the first thing you see is pretty much all the overloads with all the details right away. But let's do this slowly. First of all, most of the algorithms, not all of them, we'll come to that, are defined in the algorithm header. And then, indeed, it looks a little scary, but in total, there are just 4 overloads, which have changed over the standards. So you do see that the first algorithm has a little difference since C+17, which is essentially a const expert. So it's just 4 functions. What we're going to do is just to naively use the first one to get a little warmed up. So I now use the min element that takes 2 parameters. And that's what all the algorithms very commonly do. They take 2 iterators, in this case, forward iterators. What forward iterator is, this is what Nicola Sutis will talk about at 2 p.m. So we call min element and pass the range of elements. So the beginning of the table and the end of table. And it returns an iterator to the smallest element, so the youngest person in our example. Good. This is simple, but unfortunately it doesn't compile just yet. There's a little more to that. So if you now go back and scroll down to almost the end of the page, you'll actually find a possible implementation. I should say that this is not the implementation that is used everywhere, but it's an implementation that is reasonable. It definitely shows what's going on. So this implementation pretty much looks like what Bart has implemented before. It does a comparison of the iterators. By convention, if there's nothing, we return last. It picks the first element as a first good guess, goes to the next one, and then continues on. And then, and that's the point here, it does a comparison by means of less than. Less than. This is a pretty reasonable default, but not all types can or should be compared by less than. In particular, persons probably are not good candidates for less than operation. Now, if I would tell you, person A is less than person B, I think you would not really know what I have in mind. It doesn't really make sense. It's not intuitive, it's not a natural relation. And so some types just cannot be compared with less than. So this algorithm doesn't work for all parameters, for all types, I should say. But this is why we have overloads. The third overload of this min element actually takes 3 parameters. It takes 2 iterators again, but it also takes a compare operation. So this compare is just anything. Yeah, really, this could be a function pointer, it could be a function object, it could be lambda, it could be anything. And this compare operation now gives you the ability to deal with this comparison. You define from outside how the comparison should work. So the comp object is called, the 2 persons are passed, and if this comp object returns true, then you found a new youngest person. If it returns false, you just go on to the next one. That's simple, that's nice. And it gives you a lot of power, it gives you the power to configure this algorithm to your needs. Okay, now as somebody who likes to talk about software design, I have to point this out. This is an example for what we call a strategy design pattern. We also commonly call this policy-based design, but it basically is a design pattern right here. So, meaning we just have to pass one more parameter. So we still pass begin and end, but we now also pass, for instance, a lambda. That now looks a little more scary again, but essentially it's pretty straightforward. You have just to follow the convention. You pass something that takes 2 persons and does a comparison. In our case, we need a comparison of age, so we just compare the age value of the 2 persons. And that works. And this is good. Maggie likes that, because it's definitely easier to read. Now, of course, skeptics like Bart at this point would say, this is not easy to read. However, please do not confuse complex with unfamiliar. For many people who do not use algorithms, this is unfamiliar. But once you get into the habit of using them, it becomes familiar, and suddenly it's really easy to read. You know exactly where to look, and this is nice. And so it's also easy to understand much more quickly. It's also much shorter. Instead of in a type slide, we now have a couple of lines because I formatted it for the slide. Essentially, it's one statement. This is nice. It's also super difficult to get something wrong. So in other words, it's easy to get right. So I wouldn't know how to mess this up. It really is pretty difficult. And it's reusable. So min element is something that you can use for all kinds of minimum elements, not just for youngest persons. Good. A lot of good points. However, as Lisa now perfectly points out, we can even do better. So what I've just shown you is the classic algorithm, the C++98 form of the algorithm. It is great, but today, actually what I recommend, and Lisa would do the same thing, is the ranges min element. Now, let's take a look at CP reference first in order to get a little bit of an idea. So first, from an include point of view, you don't have to change anything. You just include algorithm, just as before. Then, okay, admittedly, this looks scary. It does. That's, from my perspective, the one big disadvantage of the ranges forms. Unfortunately, now you have to know about concepts and potentially forwarding references and about there's so many template-related things. The use is great. Yeah, so stay with me. So we have one form of min element that takes 2 iterators again. The only thing that I now quickly point out is that they don't have to be the same type anymore. So we have an I and an S, and this gives us more flexibility. Good. Then we take a comparator and something that is called a projection. I'll show in a second how this works. But then there's a second form, which is really interesting. Yes, I know that this is hard to understand and read, but this R here, that is some range. Something with begin and end. And this is now what we're going to use, because this makes the code so much more pleasant to look at. So main element now just doesn't take begin and end, it takes the vector itself, the range, the thing with begin and end. Then as a comparator, we now use less. Exactly the thing that didn't work before, because I'm now also throwing in one of these projections. I don't want to compare persons as persons, I actually want to compare the age value of a person. And so all I'm now doing is I'm projecting persons onto their age value with this. So you basically, at this point, provide a pointer to member. Is this nice? I think if you show this to somebody who has not seen this before, this person might actually, this developer might actually guess what this is doing right away. This is amazing, absolutely amazing. And so you can imagine that why this is better. There's even one more thing that we can do, because unless it's the default anyway, we can shortcut this to just an empty set of braces. So it's even shorter. And it's even harder to misuse. There is no begin, there is no end. I really would not know how to mess this up. This is correct, kind of by design. Good. And now that we have this, the comment is totally superfluous. We can just remove that. People can read that. And Maggie is super happy. All right. So first impression, but let's, of course, the quote from the expert, the quote that everybody in the community knows, and so you should know it as well, the quote from John Parent from a talk in 2013. A talk is called C+ Seasoning. So this is what John had to say in this talk. If you want to improve code quality in your organization, I would say, take all your coding guidelines and replace them with one goal. No raw loops. This will make the biggest change in code quality within your organization. Perhaps you have a little bit of an idea why that is. And we came from a very complex code that was hard to understand to something that is hard to misuse in any way. This is brilliant. This is really better code quality. All right, but next little task, Bart has a new idea, because he's not convinced just yet. Now let me put all the children to the beginning of the vector. Okay, Bart starts to code again. First, he just picks the begin and end. I calls them first and last, why not? Then he does a while loop. Bart now wants to find the first adult in the vector. So we now traverse the elements while we are not at the end. That's this part. And while we have a children, and you define yourself what child means, and so we move on as long as this is true. So indeed, we continue until we hit the first adult. Now, if I explain it this way, I think everybody nods and say, yeah, sure, this is clear. But if you would have to read this, I'm not sure if you would immediately understand what this is doing, because it's kind of counterintuitive. It says is child, but actually we're trying to find the opposite. We're trying to find an adult. It's kind of weird. Okay, then if you're not at the end, we just continue with the remaining elements. Now, first has been incremented to the first adult, so we now continue with the next element, the next person, till the end. And check, oh, this is a typo. So check is child, of course. Is child, so if this is a child, then we swap. So first currently is at the first adult. We have found the next child, so we swap. And go on with the next element. Okay, so this works, right? Does it? Are we sure? It's hard to say, right? Again, it's not a lot of code, but it looks complex. It looks difficult to understand. So again, of course, Maggie is a little disappointed. This is not really what she was looking for, or hoping for. But let's try to make this better. Yeah, because again, definitely there's something to improve. There's again a comment, and if there's a comment that tries to explain what is happening, there is something wrong. So let's look for patterns. These 3 lines here. This is a very common pattern indeed. A pattern that we use all over our code base. This is essentially a swap. However, it's a special swap because we don't want to swap iterators. We want to swap the thing behind the iterators, the persons. So that's an iter swap. That's an algorithm. Nice. So the code gets a little shorter. The while loop. I would say the while loop is again a very, very common pattern. We're trying to find a specific element. We're trying to find an element that is not a child. Find an element that is not. That's a find if not. So we try to find the first element that is not a child. Nice. Again, a lot of complexity has just vanished, has disappeared, and it's readable. So there are a lot of little algorithms hidden in this piece of code. But still there is the, nice side remark. We can pass the function pointer here. This is okay, this will compile and work. But without going into too much detail, it is advisable to use some function object like a lambda. Has to do with performance. Yeah, this is easier to inline for the compiler, so it really is advisable to use a lambda, although it essentially also just calls isChild. Now, for more information, please see core guideline 240. But essentially, we are not there yet. It still is quite a block of code, and the comment still indicates that it can do better. This entire construct here is just to put all the children to the beginning and all the other persons to the end. And yes, that's another algorithm. That looks like a partition. And it really is. So instead of doing all of this stuff manually, we just call partition. From first to last, again, and then we pass a lambda that just tells the partition algorithm what do we consider to be the interesting kind of person. So we are looking for children. So partition takes a look at all the elements, and all the elements that adhere to this given predicate, or isChild lambda, all of these elements are put to the front, and all the other elements are just put to the back. Very simple. So it's not a sort or anything. This is what we call a partition. And I would claim, I think other people would too, that this is just common terminology for all C++ developers, probably even beyond C++. Everybody should know what a partition is. And so if you now see this code, you should immediately know what this is doing. This is just putting all the children first. But you also realize that algorithms are just using algorithms. So it's a building block. Yeah? Little algorithms are used in bigger algorithms that are used in even bigger algorithms. That's good software design. And so you can use the standard algorithms in your algorithms in order to just create bigger, more complex things. Great. Again, though, we can do better. We can use the C++20 form. So ranges partition. And of course, the difference seems to be a little small, but again, we don't have to pass begin and end. We pass the vector right away. And we don't have to fiddle with begin and end anymore. Pretty cool. And again, it's easy to read. It's easy to understand. As soon as you know what a partition is, this is kind of trivial code. This is great. It's definitely not verbose. It's, again, one statement, and just to do formatting 4 lines of code only. It's super easy to get right, and it's perfectly reusable. Perfectly reusable. Let's imagine that we do not want the children first, but say the senior citizens. All we have to do is to make a change in one little place. Amazing. That's usually the hardest thing that we do in code, changing things. And if you can do this simply, I would say this is a really, really amazing improvement to the complex form that Bart implemented first. That's perfect reuse, indeed. However, Bart is always the critic. What if I wanted to keep the previous order of the senior citizens? Could I do this as simply? Well, we don't have to reinvent anything. We don't have to re-implement everything. That's the perfect opportunity for another kind of partition, something that we call stable partition. Because there's not just one partition algorithm, actually there's quite a lot of them. So if you go to CP reference again, you'll find that partitioning operations is, well, quite a sequence of algorithms. Partition is one of them, so it's ranges partition, but there's also something called partition copy and stable partition. And partition point is partitioned also. There are many of them. Many of them, they always carry the name partition in the name. And this is good, because it is terminology that everybody will understand. It is something that we can use to communicate in code. This is great, it's consistent. And all of these different partitions are just separated by means of different prefixes or suffixes. So the stable prefix tells you, I'm going to keep the previous order of the first group and the second group. And again, this is something that is very recurring in the algorithms. You will find that there is at least one other stable algorithm, stable sort, that has the same property. A stable promises you that the previous order of, in the case of sort, equal elements is kept. Good. So all of these prefixes and suffixes have fixed meaning. And so we have a very consistent naming. Very, very good. Although I should admit it's not perfect. There are a few algorithms that are not perfectly named. Yeah, we should rename them or provide something else, but it's pretty good. Yeah, there's more reason to be happy than not. Even Bart agrees. This is pretty cool. However, Bart kind of has a new challenge. What if I now wanted to put the senior citizens last without changing the order, based on the stable partition we have called before? Now that is a rotate. Okay, and this is now again a quote from this talk. You have to understand that I have to put this in this talk too. And that's a rotate is something that you have to say in every algorithm talk. But it really is a rotate. So we now take the return value of stable partition, gives us the so-called partition point. And so this is the beginning of the second group, or of course, also the end of the first group, and we put this into the next algorithm. So we rotate from everything from begin to end, such that this pass is the new first element. Nice. It's a single function, it's super clear, and it works. However, although it's simple and elegant, of course, what would happen if we would pass last? What if we would do this? Oh, that would be UB, undefined behavior. All these algorithms have some preconditions. Rotate, for instance, expects that you pass begin and end, so the complete range is the first and the third parameter. The iterator in the middle is supposed to be something valid in the range from begin to end. Now, in this case, it's kind of simple to mess this up because most algorithms take begin and end first. And if you pass last, unfortunately, you have now specified that the range is from begin to pass, and end is not inside the range from begin to pass, at least not likely. Yeah, it's very unlikely. So this is a bug. So in other words, there are a couple of small pitfalls that you have to remember. This particular pitfall, though, does not happen if you use the C++20 form again. Ranges rotate. So you just pass the table and pass, and everything is perfect. And so this is why I would definitely argue, prefer to use the new forms. They're a little more flexible, they can do more, and they also protect you from the few problems that we may have with the old algorithms. Okay, third problem. Now Bart wants to sum up the age of all persons. That's simple, right? That's just a for loop. So we start with the total age, and age was int, so we have a total age of int. And then there's a for loop. Of course, a range-based for loop. We traverse all the persons in the table, and we just add the age value. Oh, total age, sorry. Total age here, and we print the total age. Cool. That was simple. And even Lisa is not entirely against that. It's not entirely bad. It's short, it's clear, but We could also use an algorithm here. We could use accumulate. Accumulate. So now this is one of the first algorithms that is not in the algorithm header. It's in the numeric header. So there's something to keep in mind. There are a couple of special algorithms that are a little more numerical. They're in a special place. And then accumulate itself takes two iterators and an initial value, init. So essentially, we have to tell accumulate where it starts. This init is the thing that it uses to accumulate. There's a second form, however, that allows us to also additionally provide a binary operation. So why is that? Well, let's again take a look at the possible implementation. So the first accumulate is really nothing but a for loop. A simple for loop that goes through all the elements and adds onto this init value, ignore the move, not so important, all the elements of this range. All right. But again, this does not work for our purpose because we don't want to add persons to integers. Doesn't really work. Now we could add an addition operator, that the default, we could say int plus person, write an operator for int plus person, but this is not really natural again. It's not really intuitive. And that's why accumulate also comes in the second form. So we provide a binary operation that allows us to reduce these two elements. So we pass the init value and the next person to this operation, and this operation gives us the next value. And so we do this for all the persons until we have a final value. So we accumulate, reduce all of these values. The one thing that you now have to kind of remember is that op doesn't change any of these inputs, it returns a new value. It really is like an addition operator. But once you kind of understand that, it's not so difficult to do the right thing. So we call accumulate, we pass begin and end, we pass the initial value. For some, the value 0 is not entirely bad, so this is pretty reasonable, of course. And then we pass this addition operator, again, commonly done by means of a lambda. So the order is important. You first pass you have a parameter of the type of the accumulator, so int in our case. Second is of the type of the parameter, or of the values in the vector, person, and inside you just do the according addition, h plus p dot h. Great. And this is what we could print, of course. So this works. But now, of course, the skeptic part is like, how exactly is this better? The for loop was simpler, right? It was less code. And this is definitely something that you will hear a lot when you start to use algorithm. How is this really better? However, there is a pretty strong argument in this case. Look at the const. Indeed, before with the for loop we couldn't make this const because the h value was changed. But now we can actually make this const. And this avoids a very common anti-pattern, the so-called ITM anti-pattern. ITM standing for initialize then modify. Initialize and modify is this usual, and so this is the anti-pattern that Conor Högström talked about a couple of years ago very often. So it really is an anti-pattern. It's the anti-pattern that you first have some local variable and change it throughout the function, and then eventually you do something with it. Most of the time, however, we can implement this setting it once and then reading it only. This is good. It again makes the code easier to understand, it communicates, and it is a safety mechanism, of course. So, prefer to keep things immutable, and the algorithm kind of gives you that for free. This helps, definitely. This is good. Bart is not convinced yet. And he asked the one question that you also hear a lot when you start to use algorithms. What about performance? Performance. Of course, as a C++ developer, this is something that many people care about. And of course, the usual argument is, isn't the for loop faster? It's simpler, right? So it should be faster. Okay, challenge accepted. Let's compare the two solutions, the for loop with the accumulate. And I don't do a benchmark. It's actually something far simpler in this context. we can just take a look at Godbolt. So this is now perhaps a little small, I apologize, but this was the only way to make this work. So on the left-hand side, we have the sum function that takes a vector of values, and we use a for loop to sum up all the values. In the end, we return the final result. Okay, simple little function. On the right, you see the according assembly code. I'm using Clang 16, which doesn't mean that this is the one. It's just an example, and it worked out well for me. And of course, I use optimization. That's a little bit the point here. We want it to be fast. All right. Now, next slide, I'm kind of doing the same for accumulate. So I kind of have the same function signature. Again, I have a value. Oh, I could have gotten rid of this, and I return the result of accumulate. Okay. But watch the right-hand side. And I'll go back and forth between the two versions a couple of times. Watch the right-hand side. So I go back and forth and back and forth and once more, and there's no difference, right? There's no difference. It's the same code. Okay, a little less colors, I know, but it's the same code. So it really doesn't make a difference for the compiler whether you use the algorithm or the for loop. So basically you can choose whatever is more expressive, whatever is better from a coding point of view. Amazing. So there is no performance argument in this case. Absolutely not. Wow, they are fast and elegant. I'm deeply impressed. I'm still wondering why accumulate is so complex. And indeed, accumulate perhaps is a little special. It feels a little complex for what it actually does. It could be simpler, absolutely. However, this is now again perhaps a little reminder where it comes from. So the original SDL paper from 1994 actually proposed something that was a research library at that time. A research library for generic programming. And the goal was to make things generic, general as much as possible. Accumulate actually turns out to be the most generic, perhaps the most general algorithm that we have in the entire SDL. And really, you can do amazing things, not necessarily useful or good things, but amazing things with that. And as it has been demonstrated by Ben Dean in 2016. So he has spent 60 minutes on just talking about what accumulate can do. So you can actually use accumulate to find things, even to sort things. And no, I would not advise to do it. But it is possible because of the way it is implemented. So, okay, it may not be as simple as it can be, but it is amazingly powerful. Cool. And it's perfectly reusable again, of course. So let's use this on a vector of floating point values. And indeed, we now have a vector of doubles. And we just want to sum up all the doubles, yeah? Begin of the values, end values, 0. And there it is, another bug. It really happens easily. The initial value. The 0. There is a little oddity about accumulate that you please should remember. I glanced over this before a little bit. So now let's take a closer look at this. This initial value is deduced, so this is some t. Can be int, can be double, can be something. In other words, the thing that you pass, the value that you provide, that defines the type of this t. But this is not just it. This t is now used as a return type. So whatever you pass to accumulate will be the return type. That's actually part of why it's so powerful. You can pretty much decide how it works. But unfortunately, this also means that you have to pay a little bit of attention which value you provide. So 0 is definitely not the right choice for accumulating double values. So what you should definitely do is to provide something like 0.0. Or if you're lazy, .0 or 0 dot only, but you have to provide a double value. Now, since this is a common trap, a common pitfall, perhaps there is one more thing that we can do to improve on that. I would propose that, well, not just me, even Lisa would propose that you explicitly mention the type at this point. So instead of passing a literal, you pass, for instance, double empty set of braces. And it does the same thing, but it makes the type that you provide more visible. And so if somebody comes along and does a copy and paste, and unfortunately this is still done a lot, then it's not the 0 that is copied along and forgotten, it's the type, and because it's more visible, perhaps the other person will adapt this accordingly. It's slightly safer. All right. What if I now wanted to speed this up with many threads? Another performance argument, of course. Well, then unfortunately you're out of luck with accumulate. Accumulate promises, and this really is a guarantee, that everything is summed up or reduced from left to right. This is a strong guarantee, which actually you can, of course, also utilize to your advantage. So if you have double values, you could sort them from small to large, and you could sum this up from the small to the large, and this would be more accurate. Of course, this is good. But you can still parallelize. You would use C++17 reduce instead. So reduce. Reduce is super similar to accumulate. It's also, first of all, in the numeric header, of course. But then it really looks the same. It has the same interface. Yeah? 2 iterators and an initial value of type t, which also makes the return type. But reduce does not promise anything. It doesn't promise that anything is wrong. It doesn't promise that it sums up from left to right. Any order is possible. There's another overload that actually will come in handy in just a bit. You see that we only pass first and last, and that the init value is kind of chosen automatically. Nice. But the thing that I'm now after is the second overload. We pass first and last, but before that, we pass an execution policy. And that's a pretty amazing detail. Execution policy. You'll find out about the execution policy at the very top of the algorithm page, and that explains what possibilities you have. So today in C++20 we have 4 different execution policies. First, seek, sequential. Okay, that's the default. It's nothing special, nothing different would happen. We have par, parallel, thread parallel to be precise. We have par and seek, parallel by threads and by means of instructions, so SIMD operations. And in C++20, we also have unseek, so you could parallelize by means of SIMD instructions per se. And all you now have to do in order to make this parallel is to just provide an execution policy. So we would call reduce with, for instance, .execution par. And that's it. And then we would provide begin and end, and potentially, if you want to, also an initial value. That's it. That's all you have to do in order to make this accumulation, this reduction operation, parallel. It's so simple. It's so... Again, you cannot do anything wrong. Of course, the HPC enthusiast is a little disappointed because there's very few knobs to do something. You cannot explicitly pin the threads, you cannot explicitly deal with the details, but this is good enough to just make it parallel, to just speed it up. It just works out of the box. Pretty cool indeed. Of course, I said this before, for reduce, you can also just drop the initial value, which makes it even simpler. Yeah? You cannot accidentally use the wrong initial value here. And that's pretty cool indeed. Yeah, so even Bart loves this quite a lot. Now going back to this quote. You remember that John Parent explicitly said, no raw loops. This is something that you will hear a lot in the community for good reasons. I've now realized it's simple, it's correct, it's efficient, it's a wonderful all-in-one package. But although we now agree that this is good, does this mean that we should not use for and while loops anymore? Is it bad from today's perspective to use a for loop? Well, this is what many people kind of claim. And of course, there are good reasons to use them. But even in the talk of Jean, there are some answers. So, okay. Examples. So let's assume that we want to just print the persons. Now let's assume we have some output operator for persons. Okay. We could actually do this with a copy, std copy, an algorithm. We'd provide begin and end, but now copy needs another range that it copies to. I want to print this, so we now have to a little artificially pretend that we have a range with an O-stream iterator that we pass C out, and perhaps something as a delimiter. Okay, it works. It's not particularly beautiful. We could also alternatively use a for each. So we could use begin and end again as the first two parameters, and then provide a lambda that, well, prints the given person. Also okay, but definitely much more code than a range-based for loop. This is simple. This is short. So why not just use that? However, as Lisa now tells us, it definitely helps to know the algorithms, but it's not forbidden to use for loops. No. And this is kind of the definition. So if they're simple and short, everything's fine. This is what you'll find in the C++ seasoning talk, in the first half hour. There's more in this talk, but there is actually a slide that defines what a raw loop is. And not every loop is a raw loop. You can definitely use for loops if, that's right here, if it is short and simple. If people can take a look at this and understand immediately what's going on. So, if, for instance, you have just a single statement, perhaps two function calls, perhaps also successive function calls, so if you combine them, this is okay, this is fine. So, this does not mean that for while loops also are bad, but they should be simple, they should be understandable, they should be maintainable. And perhaps to give another expert a chance to also have a say, Tony van Oort defined it this way: 9 times out of 10, a for loop should either be the only code in a function, or the only code in the loop should be a function, or even both. So simple for loops are perfectly fine, perfectly okay. And now I just love these algorithms. But there's so many, more than 200 in C++20. How can I learn more about them? Well, this is an excellent question indeed. And there are a couple of great talks to watch to continue the journey. So first of all, I mentioned it a couple of times by now, I would recommend C+ seasoning, the first half hour. There's actually more in this talk. It's kind of 3 topics that I addressed, but the first half hour has become probably the most well-known. This is a fantastic example for why algorithms help. That's kind of the, I would say, the initial talk that showed the community why they're just great. There's another talk, though, that I really recommend, 105 SDL Algorithms in Less Than an Hour by Jonathan Bocara. Very famous talk indeed, but for very good reasons. This is not a talk, so don't be afraid to watch this. Yeah, 60 minutes, 105 SDL algorithms. He does not do an algorithm in 40 seconds each. No. What he's doing is he gives you the overview. Now, which algorithms are available? And this is prior to C++20, so it's half of them. Yeah, C++20 kind of doubled the number. This gives you the overview which algorithms are available, how they're connected, how they interact. And after this overview, I believe you kind of have an idea what you can use, what is available. If you're a little more into how to use them, how to apply them, then I would recommend Algorithm Intuition from Connor Hoekstra. Actually, this is 2 talks. This is part 1 of 2. And there's, of course, a second part. But he tries to actually use them for, well, problems. This is a great way to see how they also interact. Sometimes you have to use several algorithms. Sometimes you have to combine them. But the resulting code is really, really nice, really readable and intuitive. He also, this is a specialty of Connor, compares this with other programming languages. And the nice thing is C++ is not bad indeed. He concludes that what we have is a really wonderful tool. So, the guidelines and takeaways: don't be like Bart and write all of your full while loops manually. Prefer to use algorithms. Ouch, this hurts a little, but I see that you're right. Algorithms are simple, elegant, fast, and remove so much potential for errors, which is the last point alone, definitely a reason to take a closer look at this. Then please prefer to use the C+20 ranges algorithms. They're even simpler. They also give you a couple more options. It just requires C+20 compiler. And to what I've heard, still a lot of people cannot use C+20 yet. So do use algorithms, and as soon as you upgrade your compiler to C+20, just take a look around and upgrade to C+20 ranges algorithms. Then, remember the conventions and a few pitfalls. There are definitely conventions. I mentioned most of them, or a few of them definitely, but there are unfortunately also a few pitfalls, especially in the old version. Please just remember them, and then everything should be great. And so learn more about algorithms. It really is, from a strategic point of view, one of the best things that it can do to improve the quality of your code. All right, now there's only one last question. One last question because, else you hang out the entire day and you don't know what to do. Okay, I know, you would use Google, but we can clarify this right away, and I think then you can sleep well also. So, who is Jeff Albertson? I know, this is what you have been asking yourself the entire talk. Yeah, this is why you looked so confused a little bit. Everyone is known except for this one. Okay, who's Jeff Albertson? Okay, I knew it. I'll help you. The comic book guy. All right, thank you. So we have a couple of minutes for questions. If you have any, please feel free. So, hello.
Hi, great talk, thanks. Can you go back to the slide?
Partition. Okay. Perhaps this is quicker. Oh my. I did not practice where exactly my slides are. So this, okay, partition, range is partition, right? No, not yet. No.
Oh, that's fine, that's fine.
This one.
My question is, you said that I should put a lambda for a function object.
What should it not be directly? I didn't get it, sorry.
Where the lambda is, I could just write this chart.
That's correct. You could pass anything that is callable, that takes a person, of course, or something that's convertible to, takes a person. You have persons, something that you could convert to, but it must be callable. That's the convention. This is what the algorithm uses inside. I said that you should prefer lambda, though, because really this makes it easier for the compiler to inline the call. So the calling is child directly might end up with really function calls. The lambda here will be inlined definitely. So it's a performance argument, not what you can do.
Okay, so it makes it easier to inline.
Yes. Yeah. Hi.
I've noticed a convention both in your books and here that you use begin my table, end my table, as opposed to my table dot end, my table dot begin. Is there a specific reason why you prefer that form over the other one?
There is a reason. If you use dot begin, then you always assume this is a container with begin and end member functions, which is great. I think this is what we use most of the time. But now let's assume this perhaps a little weird reason that we have to use a built-in array. A built-in array would not have member functions, doesn't have any members. With begin, so the free function begin and end, this would still work. So this is a little more generic. And it kind of shows that free functions are, I would say, the backbone of generic programming. This is how it just works better. Yeah.
Thank you.
All right.
Does stable partition maintain the order of both the elements that meet the predicate and don't meet
Yes.
the predicate?
Yes, it does.
So could you have, instead of using a rotate at the end, put is not senior citizen?
Yes.
And then you wouldn't have to move.
Yeah, absolutely. You are correct. I could do that too, but very strong reason. I had to show rotate. Yeah, that's a rotate. I worked hard to make this happen. So hi.
Hi, I want you to know I have who is Jeff Albertson, big letters down on it. But also I hate you answer my question with the arrays, but is there a reason I can't just lazily pass
Yeah, exactly. This is why one of many reasons why I said that the C+20 forms are better. This is less fuss for you. But if for some reason people have to use the old versions, want to use them, perhaps sometimes you just want to sort half of the range, not the entire range, then I would prefer the free functions for the reason I just explained. Yeah. All right. Right.
Thank you for the remark. I have a question. You said it's better to call the child from a lambda instead of passing it directly.
Yes.
Can you just dive in why?
So it is a performance argument. If you use isChild directly, I didn't show it, I admit, but let's assume it's a function, plain function, then you would pass a function pointer. Any kind of pointer for the compiler is an obstacle. It cannot inline as easily. I do not claim that it never inlines. That is wrong. Sometimes it definitely happens, but it's harder for the compiler. And so it definitely helps if you just wrap this in a lambda, then it will be inlined with 100% guarantee. As soon as you go to 1, this is inlined. It's so simple.
Okay, another question, sir, is that when you call reduce, it's not very clear for me to read adds the elements binary. So it's not intuitive, I think, because it's called reduce, like accumulate. It's okay, it's accumulating, so it does an addition.
This form. Oh.
Yes, exactly. Yeah. Here the SCD reduce, for example, I think here it's not very intuitive that it adds the age.
Okay. I agree. It's names. Generally, addition, multiplication, we call them reduction operations. It's kind of a computer science term. So from that perspective, reduce is a nice term, but it's not clear that the default is addition.
Yeah, exactly.
Yeah, I agree. Perhaps this is just one thing that you have to remember, keep in the back of your mind.
Yeah.
If accumulate is not wrong. You can use accumulate too. Just remember that it's not parallelizable.
If you pass here after the double SCD plus.
Absolutely,
Yeah.
it definitely would work. Yeah.
Thank you.
All right. So, hi.
Hi, thanks for the talk. So you showed one global assembly comparison for one algorithm, right?
That's true.
But I kind of don't want to do that for every algorithm,
No.
right? Should I, in general, assume that the algorithm is as good as, if it's not better than, the unwritten code? And if there's any performance pitfall that I should be aware of?
So I would assume, yes, it is as good. But if you truly are worried about performance, the one thing that you have to do is to benchmark. Yeah, this is the one and only guideline that I can give you. So if you're worried, benchmark. And if you do find that the algorithm is not as efficient, if your for loop, whatever, is better, then first think about whether you perhaps can exploit a special case. And of course, use your for loop. But please do not just leave the for loop in some other code block. No, make it a separate function, perhaps implement it in an algorithm-like fashion to enable reuse, and give it a good name, of course. But if you feel like this is the general case, I have a better solution, and you're convinced that everything's correct, then why not file a bug report with your compiler vendor to say, actually, this is not as good as I want it to be. I think there's a perfect legitimate reason to do that. Yeah, all right. Hi. Oh, this is something I missed. Very good question, thank you. There's not. There is not. In C+20, the numeric algorithm, so everything in stood numeric, was not upgraded. The reason is, to my best knowledge, just time. They didn't have the time to do that. So no, unfortunately not. Yeah, all right. Das ist C+23. Yeah, oh, but okay, I should mention this too, thank you. In C+23, add-on, we have them, but they have different names, fold left, fold right. Correct, thank you. All right, with that, have a great day, enjoy the conference.